All right, so you know I love a good space mystery. And, well, this one involves our very own star, the sun.
Oh, yeah.
We are taking a deep dive into the latest from the Solar Orbiter mission, and get this, we're talking the sharpest images of the sun's surface ever captured, ever. We're going to zoom in on sunspots, untangle the secrets of the solar wind, and even get a glimpse of how the sun's magnetic field shapes everything around it.
You know, it's incredible. It really is incredible how much the sun impacts our lives here on Earth, even from 93 million miles away. Like just by studying these images and data from the solar orbiter, we're not just learning about our own star, we're getting clues about how stars work throughout the universe.
Okay, so the solar orbiter is giving us a front row seat to the sun's photosphere. That's the visible surface we all know and love. But what's really cool are these details called granules that we're seeing for the first time in such high resolution. They're like, giant bubbles of plasma, each one spanning hundreds of miles.
Yeah, and it's kind of like when you watch a pot of water boil and you see those bubbles rising and falling. It's like, but on an astronomical scale, that's convection in action. Hot plasma rising from the sun's core, cooling at the surface, and then sinking back down. It's constant churning. That's how the sun transports heat and energy.
Now, amidst this bubbling sea of plasma, you can't miss those dark patches, the sunspots. They look almost calm, but they're actually a sign of some pretty intense magnetic activity, right?
Exactly. Think of the sun's magnetic field as a giant tangled web, and sunspots are like knots in this web. These tangled magnetic fields disrupt the normal flow of plasma, kind of like creating a bottleneck. And since that hot plasma can't rise to the surface as easily, the sunspot appears cooler and darker.
Okay, that makes sense. But it's not just about the temperature difference, is it? I mean, these magnetic fields are doing a lot more than just creating a few dark spots.
Oh, you're right. You're absolutely right. The sun's magnetic field plays a huge role in shaping its behavior. It's what drives those massive solar flares and coronal mass ejections that send blasts of energy and particles out into space.
Ah, so we're talking about the solar wind, that constant stream of charged particles that actually reaches us here on Earth, right? And I've heard it can have some pretty interesting effects.
Absolutely. Sometimes those effects are beautiful, like the auroras that light up the sky near the poles. But the solar wind can also be disruptive. Like imagine those coronal mass ejections, like a giant sneeze from the sun hitting Earth. That surge of energy can knock out satellites, disrupt GPS and communication networks, even cause power outages.
Wow, that's a sobering thought. So understanding the sun's magnetic field and those sunspots isn't just about satisfying our scientific curiosity. It's about protecting our technology and infrastructure here on Earth.
Precisely. And that's why the solar orbiter's magnetic field map is so valuable. It gives us a detailed view of the sun's magnetic landscape, showing us where those intense magnetic fields are concentrated and helping us predict potential solar storms.
So it's like having a weather forecast.
Mm-hmm.
But for space weather, that's pretty amazing. But hold on. There's another image that I found fascinating. The one that shows how material on the sun's surface is constantly moving. It's called a tachogram, right?
Yes, the tachogram is like a snapshot of the sun's motion. It uses color to show us how material is flowing. Blue areas are moving towards the spacecraft, and red areas are moving away. What's really fascinating is that we can see how material is being flung out around sunspots, giving us clues about how the solar wind is generated and why it travels so fast.
It's like the sun is constantly throwing these little parties around the sunspots, with plasma swirling and shooting off in all directions.
That's a great way to visualize it. And by studying these patterns of motion, we can start to understand the complex forces at play on the sun's surface. It's like unraveling a cosmic dance.
Speaking of cosmic dances, what about that breathtaking image of the sun's corona? That ethereal outer atmosphere. It looks so delicate in the pictures, but I know it's anything but calm.
Yeah, the corona is a region of extremes. It's incredibly hot, millions of degrees hotter than the sun's surface, and it's where the solar wind gets its final push out into space. The images from solar orbiter show us these delicate-looking strands of plasma, tracing out the sun's magnetic field lines.
It's almost as if we're seeing the sun's magnetic skeleton, and those field lines are like highways for the solar wind to escape.
Exactly. And those escaping particles, they eventually reach us here on Earth, interacting with our planet's magnetic field. That's what creates those beautiful auroras. But it can also trigger those geomagnetic storms we were talking about earlier.
Yeah.
So understanding the corona is crucial to understanding how the sun affects us here on Earth.
Wow. I'm starting to realize just how interconnected everything is. The churning plasma on the sun's surface, the magnetic field lines, the solar wind, and even those beautiful auroras dancing in the sky. It's all part of this incredible dynamic system.
And solar orbiter is giving us a whole new perspective on this system.
Now, speaking of new perspectives, I hear that Solar Orbiter is on a mission to capture images of a region we've never seen before.
That's right. In early 2025, Solar Orbiter will reach a higher inclination, allowing it to capture the first ever images of the sun's poles.
The sun's poles, that's incredible. What are you hoping to learn from those images?
Well, the sun's poles are thought to play a crucial role in the solar cycle, that 11-year period of fluctuating activity. By observing the poles, we hope to gain a better understanding of how the sun's magnetic field flips polarity every 11 years, a phenomenon that drives those solar storms and affects our planet.
So we're talking about getting a glimpse into the very heart of the sun's magnetic dynamo. That's absolutely mind-blowing. But before we jump ahead to 2025, let's take a closer look at what we've already learned from the Solar Orbiter's recent observations.
A great idea. These high-resolution images of the photosphere, those tangled magnetic fields around sunspots, the swirling motions in the tachygram, and that ethereal view of the corona, they're all pieces of the puzzle.
And each piece helps us understand how this massive ball of plasma, 93 million miles away, can have such a profound impact on our lives here on Earth.
Exactly. And remember, this is just the beginning. Solar Orbiter will continue to orbit the sun, gathering more data and capturing even more detailed images.
Well, I, for one, can't wait to see what other secrets the sun reveals.
Me neither. And who knows, maybe these discoveries will inspire the next generation of space explorers and scientists.
Speaking of inspiration, what can our listeners do to explore these amazing images for themselves? I mean, I'm already itching to take a closer look.
Well, you're in luck. We'll be sure to include links to all the images and resources mentioned in this deep dive in our show notes. You can zoom in on those incredible granules, trace those magnetic field lines, and even watch those mesmerizing tachygrams in action.
That's fantastic, because I have a feeling our listeners are just as captivated by these solar revelations as we are.
I have no doubt. And remember, this is just a glimpse into the vast and complex world of solar science. There's still so much to discover, so many mysteries yet to be unraveled.
And with missions like Solar Orbiter constantly pushing the boundaries of what's possible, who knows what incredible insights await us in the years to come.
Indeed. The sun, our nearest star, still holds countless secrets.
All right, you've definitely piqued my curiosity even more. But for now, we need to take a short break. When we come back, we'll dive deeper into the implications of these discoveries and what they mean for our understanding of the sun. So stay tuned, space explorers. We've got much more to uncover.
Welcome back. It's amazing to think about all the information we're getting from these images, isn't it?
It really is, and I'm still reeling from the fact that we're about to see the sun's poles for the very first time. But before we get lost in the future, let's talk a little more about those incredible mosaics we were discussing. They're not just single snapshots, are they?
You're right. You might be surprised to learn that each mosaic is actually composed of 25 individual images, each capturing a tiny portion of the sun.
Wait, 25 images for one mosaic? Why so many?
Well, because Solar Orbiter was so close to the sun, each individual image only covered a small section of the solar disk. Imagine trying to photograph a giant beach ball from just inches away. You'd only capture a small patch at a time. To get the whole picture, they had to tilt and rotate the spacecraft to capture different areas of the sun's surface, and then carefully stitch those images together.
So it's like creating a giant jigsaw puzzle, but with cutting-edge technology and the sun as the subject. That's dedication, and they're going to have to employ those same techniques when Solar Orbiter reaches a higher inclination and can finally capture those elusive images of the sun's poles, right?
Absolutely. It's a testament to the ingenuity of the mission team. But think about the payoff. Getting those polar images in 2025 will be groundbreaking.
It really makes you appreciate the effort and precision that goes into these missions. It's not just about sending a spacecraft up there. It's about having the vision and the technical know-how to capture those truly unique perspectives.
Exactly. And the results are well worth it. Imagine the insights we could gain from studying those polar regions, especially when it comes to understanding the solar cycle.
Speaking of insights, what are some of the key takeaways you hope our listeners will walk away with after this deep dive?
I think one of the most important things to remember is that the sun is not just a static ball of light. It's an incredibly dynamic and complex system, with constantly changing magnetic fields, swirling plasma flows, and explosive events that can impact us here on Earth.
And as we've seen, understanding those processes isn't just about satisfying our scientific curiosity. It has real-world implications for our technology, our infrastructure, and potentially even our safety.
Absolutely. And it's not just about us either. The sun's influence extends throughout the solar system, shaping the environments of planets, moons, and even the space between them.
So what we're learning about our own sun helps us understand the countless other stars scattered throughout the cosmos. It's really about unlocking the secrets of the universe, one image at a time.
That's a great way to put it. And it's important to remember that even with these amazing images and data from Solar Orbiter, we're still just scratching the surface. There's so much more to learn about our sun. And with each new discovery, we get a little closer to understanding our place in the grand scheme of things.
On that note, any final thoughts or words of wisdom for our sunstruck listeners before we wrap up our deep dive today?
I'd say this: never stop looking up, and never lose your sense of wonder. The sun is a constant source of fascination. And with every new mission and every new discovery, we get to experience that awe and excitement all over again.
Beautifully said. And who knows, maybe one of our listeners will be inspired by these images to make their own groundbreaking discoveries someday.
Wouldn't that be amazing?
Mhm.
The future of space exploration is bright. And I have a feeling there are many more solar surprises waiting to be uncovered.
Well, on that note, I think we've reached the end of our deep dive for today, but I have a feeling this conversation about the sun is far from over.
Absolutely not. It's a topic that will continue to fascinate and intrigue us for generations to come.
A huge thanks to you for illuminating this journey for us today.
My pleasure. Always happy to share the wonders of the cosmos.
And to our listeners, thanks for joining us on this deep dive into the heart of our solar system. Until next time, keep looking up and stay curious. It's funny, we often take the sun for granted, this giant ball of fire in the sky. But after this deep dive, I'm looking at it with a whole new sense of awe.
Yeah, it really is true. The sun is so familiar to us, yet it holds so many mysteries. And it's a constant reminder that there's always more to learn, even about the things we think we know best.
And speaking of learning, I have to ask, for those of us who aren't astrophysicists, what's the best way to really grasp the scale and complexity of what we've been talking about? It's one thing to see a picture of a sunspot, but it's another to really understand the forces at play.
That's a great question. One thing I always tell people is to try to visualize it. Imagine yourself standing on the surface of the sun, surrounded by this ocean of boiling plasma. Feel the intense heat, the powerful magnetic fields, and the sheer energy of it all. It's a humbling experience, even just in your imagination.
Okay, I'm trying to wrap my head around that. I'm feeling pretty small right now. But it does give you a sense of perspective, doesn't it?
It does, and it reminds us that we're part of something much bigger than ourselves. The sun is the center of our solar system, the source of energy that sustains all life on Earth. It's a force of nature that we can't control, but we can strive to understand it better.
And that understanding is more important than ever, especially with the increasing reliance on technology that's vulnerable to the solar storms we talked about.
Exactly. The more we know about the sun, the better equipped we are to protect ourselves from its potential disruptions. It's like knowing the forecast. If you know a storm is coming, you can take steps to prepare.
So we're not just passively observing the sun, we're actively learning how to live with it, how to adapt to its rhythms and its sometimes unpredictable behavior.
That's a great way to put it. It's a partnership in a way.
Mm-hmm.
We depend on the sun for life itself, but we also need to respect its power and learn how to coexist with it safely.
Well said. Any final thoughts for our listeners before we wrap up this incredible journey into the heart of our solar system?
I just encourage everyone to keep exploring, keep asking questions, and never lose that sense of wonder about the universe around us. We've only just begun to scratch the surface of what there is to discover.
And maybe, just maybe, some of those future discoveries will come from the curious minds listening to this very deep dive. So to all our listeners, thank you for joining us. Keep looking up and keep those questions coming. Until next time. All right, so get this. We're diving into something today that's seriously rare.
Oh.
Like 1 in 50,000 rare.
Wow. That's,
I know, right? It's like winning the lottery while getting struck by lightning, while finding a 4-leaf clover.
Uh-huh. Okay, you have my attention.
We're talking about something called the Einstein Zig-Zag. It's the first time we've ever seen a single quasar.
A single what?
Quasar. It's appearing 6 times in one single image.
Okay, now that's something I gotta see.
Imagine like a bowling ball on a trampoline. You know how it kind of warps the surface?
Yeah, sure.
So now, replace that bowling ball with a galaxy and the trampoline with space-time. That's the basic idea behind gravitational lensing.
Ah, I see. That's a pretty cool analogy.
Yeah, it is.
So what's really wild is that this warping, like Einstein predicted in his theory of general relativity, it doesn't just mess with stuff that has mass, it bends light itself.
Exactly.
It's mind-blowing.
It is. So in this case, the light from this distant quasar, which is basically a supermassive black hole that's super bright, is getting bent. Yeah, bent around not just one, but two galaxies.
Two.
Yeah, two galaxies that are lined up perfectly, like a cosmic magnifying glass.
That's how we're seeing 6 images of the same quasar then.
Yep,
And it makes this zigzag pattern.
exactly. And get this, this was all discovered thanks to the James Webb Space Telescope.
Oh, the JWST.
And this isn't just some cool picture. This perfect alignment actually helps us tackle some of the biggest mysteries in cosmology.
Oh, really? Like what?
Well, for one, there's this thing called the Hubble tension. It's basically this difference between the predicted expansion rate of the universe and what we're actually observing.
Like we're getting two different answers.
Yeah, it's like trying to measure a room and getting two totally different lengths depending on which tool you use.
Huh, that's weird.
I know, right? So the big question is, which measurement is right?
Right. That's what we need to figure out.
Exactly. And this Einstein zigzag might actually help.
Wow.
Well, because of its precise alignment, it's like the super accurate cosmic yardstick.
The yardstick.
Yeah. You see, the time delays between when the light from each quasar image arrives, that lets us measure distances and expansion rates super precisely.
Wow.
So it might help us figure out which of those measurements is more accurate or even if we need to totally rethink our understanding of cosmology altogether.
That's huge.
It is, right?
Yeah.
But hold on, there's more. We also have this mysterious thing called dark energy.
Ah, yes, dark energy. The force that's making the universe expand faster and faster.
Right. What can the zigzag tell us about that?
So imagine the universe as this car that's speeding up.
Okay.
Dark energy is like this mystery fuel pushing the gas pedal.
Hmm.
But we have no idea what it's made of or how it works.
We need to figure out its properties, then.
Exactly. There's something called the equation of state for dark energy that we need to crack. And this zigzag lensing system, it gives us a rare chance to do just that.
Okay, so this equation of state, is it like figuring out what kind of fuel powers this dark energy engine?
Precisely. By studying how the light is bent and delayed, we get clues about how matter and dark energy are spread out along its path. And that helps us narrow down the possible values for this equation.
So by knowing this equation, we can predict what dark energy will do. Like, will this cosmic car keep accelerating forever?
Exactly. Will it slow down eventually? Or could it even reverse and cause a big crunch? This equation could tell us.
Wow, okay, this one image is raising a lot of questions.
You could say that. It's pretty amazing.
It's like a cosmic Rosetta Stone.
Right. And to really grasp how big this is, we need to go back a bit. So this quasar system is called J7721 plus 88842. Get this. It was actually spotted back in 2017.
Wait, really?
Yeah.
So what's different now? Why is this zigzag such a big deal all of a sudden?
Well, back then, telescopes weren't as powerful. We could only see 4 images of the quasar.
Ah, I see.
But the James Webb Space Telescope, the JWST, it's got incredible resolution. It's revealed the full 6-image zigzag for the very first time.
It's amazing what better technology can do, huh?
It really is. And we're talking about mind-boggling distances here. The light from the closest galaxy in this system, it's been traveling for 2.3 billion years to reach us.
2.3 billion years. We're seeing that galaxy as it was before dinosaurs even existed?
And the light from the farther galaxy has been traveling for a whopping 10 billion years.
Wow.
And the quasar itself, we're seeing it as it was about 11 billion years ago, just a few billion years after the Big Bang.
We're basically looking back in time to the early universe.
We are. It's pretty amazing, isn't it?
It really makes you realize how small we are in the grand scheme of things.
It does.
And all of this is because of this incredibly rare alignment. What are the odds of finding another Einstein zigzag out there?
Well, the odds might seem tiny, but remember, we've barely scratched the surface of what's out there. The universe is huge.
So there could be more of these zigzags out there just waiting to be discovered.
Exactly. And new sky surveys, like the Vera Rubin Observatory, they're being built specifically to scan the entire sky, looking for rare events like this.
Wow. So the next step is to go on a cosmic treasure hunt and see if we can find more.
You got it.
But before we get into that, I want to know how scientists are using this current discovery. It's one thing to find it, but how do they actually use it to tackle these cosmic mysteries?
That's a great question. It's like the universe has set up this natural experiment for us.
Okay, I like where this is going.
So let's start with that Hubble tension we talked about. Remember, we have those 2 different ways of measuring the expansion of the universe, and they're giving us different answers.
Yeah, it's like the universe is messing with us.
Right. So one way looks at the early universe using the cosmic microwave background radiation, basically the afterglow of the Big Bang.
Right.
We use that to calculate the expansion rate. The other way looks at objects in the nearby universe. We measure their distances and speeds to figure out how fast they're moving away from us.
And the problem is, these two methods give us different numbers.
Exactly. And that's where Einstein Zig-Zag comes in.
Yeah.
The time delays between those 6 quasar images, they act like a really precise ruler.
A ruler.
Yeah, for the universe. So we can measure distances and expansion rates really accurately with it.
So we can check which of the existing measurements is more accurate.
Exactly. Imagine having 2 tape measures that give you slightly different readings for a table. You want to use a more reliable way to measure to see which tape measure is off. That's what this zigzag is doing for us.
Got it. So if the zigzag's measurements line up with the early universe values, then maybe our local universe measurements need adjusting.
Precisely.
But what if it lines up with the local universe values?
Then things get really interesting.
Like how?
It could mean our whole understanding of how the universe evolved, our standard cosmological model, it might need a major rewrite.
Oh.
It could mean there's some new physics happening that we don't even know about yet.
Okay, so this little zigzag could have huge implications.
It really could. Now let's talk about dark energy again. Remember that equation of state we mentioned?
Yeah, the one that tells us how this mysterious force behaves. It's like trying to figure out the personality of a ghost.
Haha. Well, think of it like this. Imagine you've discovered a brand new type of fuel. You need to figure out its properties. Does it burn fast? Does it have a high energy output?
Right.
That's what the equation of state is for dark energy. It tells us how its density changes as the universe expands.
Okay, but how does the zigzag help us with that?
You see, the light from the quasar, it doesn't just bend around those galaxies. It's also affected by how matter and dark energy are distributed along the way.
So by analyzing how that light is distorted, we can learn about the nature of dark energy itself.
Exactly. It's like shining a flashlight through fog. The way the light scatters tells you about how dense the fog is and what it's made of. The Einstein Zig-Zag is our cosmic flashlight.
And the universe is our fog.
Exactly.
Okay, I get it. But this is just one zigzag. It's
Yeah.
one data point. We need more, right? To be really sure about anything.
You're absolutely right. One zigzag, while amazing, isn't enough to rewrite the textbooks. But it's a great start.
So where do we go from here? What's next?
The next step is to find more of these Einstein zigzags. And luckily, we've got new tools that'll help us do just that.
Oh, like what?
Well, there's the Vera Rubin Observatory in Chile. It's being built to scan the whole sky every few nights, looking for changes in weird objects.
It's like a giant time-lapse camera for the universe.
Uh-huh, exactly. And maybe, just maybe, we'll spot another Einstein zigzag in one of those photos.
That would be amazing.
It would. And every new discovery like that, it gives us more data, more clues. And that helps us refine our understanding of dark energy, the expansion of the universe. And who knows, maybe even uncover brand new physics we haven't even thought of yet.
That's what I love about science. It's all about discovering new things and constantly learning.
It really is. This one-chance alignment, this cosmic quirk,
Yeah.
it's opened up this whole new window into the universe.
It's like we stumbled upon a secret passage in a giant library.
And who knows what other incredible things we'll find as we explore those passages.
That's what I'm excited to find out.
Me too. Me too. It really is. It makes you wonder what else is hiding out there.
Right. And this discovery isn't just about pretty pictures. It's actually helping scientists.
Oh, yeah, for sure. This Einstein zigzag, it's like this amazing tool.
A tool.
Yeah. It's like the universe set up this perfect experiment for us.
Okay, I like that. A cosmic experiment.
Exactly. So remember that Hubble tension we talked about? How we have those two ways of measuring the universe's expansion, but they give us different answers.
Yeah, it's like the universe is playing tricks on us.
Right. So one method looks at the early universe using this thing called the cosmic microwave background radiation.
The afterglow of the Big Bang.
Exactly. It's like the faint echo of the Big Bang. We use that to calculate how fast the universe was expanding back then.
Okay.
The other method, it looks at stuff closer to us in the nearby universe. We measure how far away things are and how fast they're moving away from us.
And those two methods, they give us different numbers.
They do, and that's where our Einstein zigzag comes in handy.
Okay.
The time it takes for the light from those 6 quasar images to reach us, those time delays, they act like a really, really precise ruler.
A ruler for the universe.
Yep, it's like a cosmic yardstick. We can use it to measure distances and how fast the universe is expanding with incredible accuracy.
So we can double check which of those two methods is closer to the truth.
Exactly. Think of it this way. You've got two tape measures, but they give you slightly different readings for the same thing.
Right.
You'd want to grab a super accurate, super reliable ruler to check which tape measure is wrong, wouldn't you?
Yeah, definitely.
That's what this Einstein Zig-Zag is for us. It's our super reliable ruler for the universe.
Got it. So let's say the zigzag's measurements match up with what we see in the early universe.
Hmm.
Then maybe our measurements of the nearby universe need some tweaking.
Right.
But what if? What if the zigzag's measurements match the nearby universe stuff more closely?
Well, then things start to get really interesting.
What do you mean?
It might mean our entire understanding of how the universe evolved, that standard model, it might need a serious overhaul.
Whoa, okay.
It might suggest there are things happening in the universe that we just haven't figured out yet.
Yeah, we're missing something big.
Exactly. So this little zigzag, it could have huge implications for our understanding of the cosmos.
It's amazing how much information we can get from one little image.
It really is. It shows you how powerful observation is in science.
Right. We can't create these cosmic events ourselves. We can only watch and try to understand what they're telling us.
Exactly. And sometimes the most unexpected things can lead to the biggest breakthroughs. Now, what about dark energy? Remember we were talking about that equation of state?
Yeah, that thing that's supposed to tell us how dark energy works. It's like trying to read the mind of a ghost, isn't it?
Uh-huh. It's tricky, that's for sure.
Yeah.
So think of it this way. Imagine you've discovered a brand new kind of fuel.
Okay.
You want to know everything about it, right? How it burns, how much energy it releases.
Right.
That's what the equation of state is for dark energy. It tells us how its density changes as the universe keeps expanding.
Okay, so how does the zigzag help us figure that out?
Well, the light from that quasar doesn't just bend around those galaxies. It's also affected by everything it passes through along the way, all the matter and dark energy.
So it's like help. The light is carrying information about dark energy.
Exactly. By analyzing how the light's been distorted, we can get clues about what dark energy is like, how it's spread out in the universe.
Okay.
It's like shining a flashlight through fog, right? The way the light spreads out tells you how thick the fog is, what it's made of.
So the Einstein zigzag is our cosmic flashlight.
You got it. And the universe is our foggy mystery to explore.
This is so cool. But it's just one zigzag, right? Like we were saying before, we need more data to be really sure about all this.
You're absolutely right. One zigzag's amazing, but it's just the beginning.
So what's next? How do we get more data?
Well, the hunt is on for more Einstein zigzags. And the good news is we've got some new tools that are going to help us a lot.
Ooh, like what?
There's this incredible new observatory being built in Chile called the Vera Rubin Observatory. It's going to scan the entire sky every few nights, looking for anything that's changed, anything unusual.
Wow, so it's like a giant time-lapse camera for the whole universe.
Exactly. And who knows, maybe we'll get lucky and spot another Einstein zigzag in one of those images.
That would be incredible.
It would. And every new discovery like that, it gives us more pieces of the puzzle, more clues about dark energy, about how the universe is expanding.
And maybe even some clues about brand new physics we haven't even imagined yet.
Exactly. This is what makes science so exciting, isn't it?
Oh.
Always discovering new things, always learning more.
It's like we're explorers, charting a vast uncharted territory.
We are. And this Einstein zigzag, it's like we stumbled upon a secret path in that uncharted territory, a path that can lead us to incredible discoveries.
I can't wait to see where it leads us next. It really is mind-blowing how this one weird zigzag can change so much of what we thought we knew about the universe.
It shows how important it is to just keep looking, keep observing.
Yeah.
You don't get to set up these cosmic experiments.
Right.
The universe does that for us. We can just observe and try to figure out what it all means.
It's like the universe is talking to us in the secret code,
Yeah,
and we're just starting to crack the code.
exactly. And this Einstein zigzag, it wasn't like scientists were out looking for it specifically.
Yeah.
No, it was a total surprise, a happy accident. We only found it because the James Webb Space Telescope is so powerful.
That makes me wonder, what else is out there that we just haven't seen yet? What other surprises is the universe hiding?
That's the best part about astronomy.
What is?
There's always something new to discover.
Mm-hmm.
And every time we learn something new, we understand the universe and our place in it a little bit better.
It really puts things in perspective, doesn't it?
It does. It makes you feel pretty small.
Yeah.
But it's also inspiring to see how much we've learned.
Yeah, it is. And it's not just about observing. Scientists are using these discoveries to actually push our understanding of physics and cosmology forward.
Absolutely. Like with that Hubble tension we were talking about.
Right.
That's been a big puzzle for scientists for years. Maybe this Einstein zigzag holds the key to solving it.
Or maybe it'll lead us to even more questions.
Either way, it's good for science
Oh,
because it makes us challenge what we think we know and come up with better theories.
right. Always testing, always refining.
Exactly. And this discovery also shows how important collaboration is in science.
What do you mean?
This wasn't just one scientist working alone, or even one team. It took researchers from all over the world sharing their knowledge and working together to figure this out.
That's really cool.
It is.
Yeah.
It shows, but even though we have our differences here on Earth, we can still come together and achieve amazing things.
Especially when we're trying to solve big cosmic mysteries.
Exactly. And who knows what the future holds? With new technology, even better telescopes? Who knows what other mind-blowing things we'll find out there?
Maybe we'll find even weirder gravitational lenses.
Maybe.
Or finally figure out what dark energy and dark matter really are.
It's all out there, waiting to be discovered.
So just to recap, we started with this one image, this bizarre zigzag.
A single quasar magnified 6 times by the gravity of 2 perfectly aligned galaxies.
Billions of light years away.
It's a reminder that the universe is full of surprises.
And that there's still so much out there that we don't know.
That's the beauty of it all, isn't
It
it?
really is. Well, that wraps up our deep dive into the Einstein Zig-Zag. Thanks for listening, everyone. We'll catch you on the next one.
See you then. Ever wonder about Earth's baby pictures?
Baby pictures.
Yeah, like a glimpse into its earliest days.
Ah.
Turns out they might be hidden in plain sight.
Intriguing.
On the moon.
On the moon.
Yeah, we're talking impact basins, you know.
Right, those massive craters.
Exactly. And today, we're doing a deep dive on a fascinating one.
Okay, which one?
Mare Orientale.
Oh, Mare Orientale, a classic.
Like a giant bullseye.
Yeah, with rings spreading out from the impact.
And what's so special about it?
Whoa.
It might hold the key to understanding Earth's own wild past.
Now that's a story I want to hear.
So why is Mare Orientale so valuable to study?
Well, for one, it's relatively young.
Young.
Geologically speaking, of course.
Oh, okay.
Meaning its impact melt is well preserved.
Impact melt, that's the rock liquefied on impact, right?
Exactly. But here's the catch.
Okay.
It's also old enough to have, well,
Have what?
other features on top, like lava flows and smaller craters.
So it's like a multi-layered record.
Precisely. Imagine trying to see a photograph that's been painted over several times.
Oh, I see. So we need to peel back those layers.
Yeah, to get to that original image.
That sounds pretty complicated.
It definitely presents a challenge.
Especially with a site as large and complex as Mare Orientale.
Absolutely. But luckily,
Exactly.
there's a new geological map.
Oh, tell me about this map.
It's helping us do just that, peel back those layers.
Amazing. What's the goal of this map?
The goal is to pinpoint those areas of original impact melt
Okay.
amidst all the
Amidst all the what?
clutter.
Ah, right, all those later features.
Exactly. And how does it work?
Yeah, how does it work?
By focusing on 2 key features.
I'm listening.
Smooth, cracked areas of the basin floor.
Okay.
They're labeled BFSC,
BFSC, got it.
which likely contain that original impact melt.
So that's one feature.
And then there's the ejecta,
Ejecta.
the debris launched out from younger craters.
Oh, the craters that formed on top of Mare Orientale.
You got it.
Okay, I see. So you're looking at those 2 features.
Right. Think of it as digging through layers of a cake.
Okay, I like that analogy.
We're searching for that original base layer
Makes sense.
among all the later toppings.
Okay, but wouldn't ejecta from those younger craters potentially contaminate things?
Ah, you're thinking about the dating.
Right. Wouldn't it mess up our dating of the basin itself?
That's a great question.
How can we be sure we're looking at the right stuff?
Well, the researchers have a clever solution.
Okay, I'm all ears.
They theorize
Yep.
that if samples from both the smooth basin floor
Okay.
and the ejecta from younger craters
Uh-huh.
show the same age,
So same age, then what?
it means that ejecta
The ejecta.
actually originated from that initial impact melt.
Wow, so it was just churned up by later impacts.
Exactly.
It's almost like a detective story.
It is.
We're using clues to piece together the timeline.
Precisely. Of course, to confirm this, we need a sample return mission.
Right, to analyze the actual rocks,
But this map gives us a roadmap.
like a starting point.
It tells us where to dig, so to speak.
I love that. So this new map allows us to create a more accurate timeline
Yes.
of lunar bombardment, which, in turn, directly informs our understanding of early Earth.
Right.
Wouldn't Earth have been hit even more?
Oh, Oh, absolutely.
because of its larger size and gravity.
Exactly. And to understand this period of intense bombardment,
Yeah.
we turn to a fascinating technique.
Lay it on me.
It's called crater counting.
Crater counting.
Yeah.
That sounds pretty straightforward.
It is. More craters equal an older surface.
Makes sense.
It's a simple principle.
Right.
Over time, more impacts leave their mark.
So by analyzing the craters on the moon,
We can estimate the ages of different surfaces.
that's so cool.
The current estimate for Mare Orientale's age
Yeah.
is 3.8 billion years old.
Wow.
But this new map could help us refine that.
Even more accurate.
What makes this so valuable
What's
is
that?
we can extrapolate that information to Earth.
To Earth's own impact history.
Exactly. A history largely lost to our planet's geology.
So the moon acts like Earth's attic,
I love
preserving a record of those early bombardments.
It's a remarkable thought.
Mind-boggling to think about the scale of these impacts
It really is.
and the effect they must have had on Earth.
It makes you wonder,
So,
could these impacts have something to do with
with what?
the emergence of life?
Wow, that's a big question,
It is.
and one we'll have to explore further.
Definitely. A question with no easy answers, that's for sure.
But it highlights the influence of these events, right?
Absolutely. On our own planet's history.
It underscores what?
Okay.
It underscores what?
The interconnectedness of our solar system, I guess.
It really does.
It's incredible to think that something like a giant impact could be linked to, the origins of life.
Precisely. We're talking about a period
Yeah.
3.8 billion years ago.
Okay.
It coincides with the first evidence of life on Earth.
So did these impacts,
They what?
did they create conditions for life?
That's the question, isn't it?
Were they destructive and conducive to life at the same time?
It's a fascinating paradox.
Did they, set the stage for life?
It's a possibility, some might even say.
Really? Like a cosmic reset button?
A reset button.
Wiping the slate clean,
I see what you mean.
allowing life to emerge anew.
That's a pretty evocative image.
Are there
Bear what?
specific theories about how these impacts
Yeah.
might have actually sparked life?
Well, there are some intriguing hypotheses. For instance, the intense heat
Mm-hmm.
from the impacts
Yeah.
could have created hydrothermal vents.
Hydrothermal vents, what are those?
They're underwater hot springs,
Oh, okay.
teeming with chemicals and energy.
And these are considered
Well,
potential cradles for life.
Even today, yes.
Wow.
They might provide the building blocks for early organisms.
So while seemingly destructive,
Mm.
these events could have created environments for life.
It's a possibility. Almost like
Like what?
a phoenix rising from the ashes.
Yeah, a powerful metaphor.
It speaks to the resilience of life,
It does.
adapting and flourishing in the face of challenges.
It's a reminder of the fragility of life as well.
The delicate balance.
Yes, the balance that allowed it to evolve.
But if these giant impacts were so frequent back then, why haven't we seen anything similar recently?
Good point. The period we're talking about,
Yeah.
it's called the late heavy bombardment.
Late heavy bombardment, okay.
It was a chaotic time.
Chaotic how?
The leading theory suggests
I'm listening.
that gravitational interactions between the giant planets.
You mean like Jupiter and Saturn?
Exactly. They caused a sort of cosmic billiards game,
Cosmic billiards, whoa.
flinging asteroids and comets inward.
Towards us.
Earth and the moon became prime targets.
So we're lucky things calm down.
Lucky indeed.
Life could evolve without constant threats from space.
Exactly. The rate of impacts declined dramatically.
But,
But
the threat hasn't vanished entirely, right?
you're right.
I mean, we've seen smaller impacts even recently.
We have
And there's always the possibility
the possibility of what?
of a larger object crossing Earth's path someday.
It's a sobering thought.
So studying the moon's impact history,
Yes.
it's not just about understanding the past.
It isn't.
It's about the future too, right?
It is. It's about informing our future.
By deciphering those clues in the craters,
Exactly.
we can understand the dynamics of the solar system,
We can.
the frequency of impacts,
Yes.
and develop strategies to protect our planet.
That's the ultimate goal.
Wow, I hadn't thought about it that way.
It's a crucial aspect of planetary science.
You've really shifted my perspective.
How so?
I used to think of the moon as static and unchanging,
I understand.
but now I see it as dynamic,
It is.
ever-evolving, holding secrets about our past, present, and future.
That's beautifully put.
It speaks to the power of scientific exploration.
It does.
Every new discovery adds to our understanding.
It's a never-ending journey.
We've been focusing on Mare Orientale
Hmm.
and what it means for Earth.
Right.
But this new map opens up new avenues, doesn't it?
It does, for exploring other impact basins on the moon.
Some even older than Mare Orientale.
Absolutely. Imagine the insights we could gain.
It's like unlocking a new chapter.
A new chapter in the history of the solar system.
It'll be exciting to see what future missions reveal.
I agree.
Speaking of future missions,
Yes.
you mentioned a sample return mission earlier.
Right.
If you were designing one
Oh, interesting.
to collect samples from Mare Orientale,
Okay.
where would you target? What questions would you want to answer?
That's a great question. One that mission planners are considering right now.
So where would you start?
Well, if I were designing such a mission,
Yeah.
I would prioritize two key areas. I'd start with those smooth, cracked regions of the basin floor.
The BFS key areas.
Exactly. Getting samples from there would give
Yeah.
us the most pristine examples
Yeah.
that original impact melt.
Ah.
We could precisely date Mare Orientale then
Yeah, okay.
and compare it to other basins.
Right.
Refine our understanding of that bombardment period.
Makes sense. But what about those younger craters? Wouldn't sampling their ejecta be important too?
You're absolutely right.
Especially if we want to test that theory.
Yeah, about the ejecta origins.
Right, that some of it came from that initial impact.
My second target would be a younger crater then,
Okay.
but one large enough
We'd have what?
to have excavated material from deep within the basin.
Oh, okay. So by analyzing its ejecta
We could determine if it matches the impact melt from the basin floor.
and confirm that link to the original event.
Precisely.
So comparing samples from those two spots,
Yeah.
we could confirm that even younger features are tied to that ancient impact.
Exactly.
Like a giant puzzle.
It is. And this approach isn't limited to just Mare Orientale.
Oh, so we can apply it to other basins.
Absolutely. By identifying and sampling key features, the original melt, ejecta, even volcanic deposits,
We could build a timeline of lunar bombardment.
a whole impact chronology.
Wow. A record of the early solar system.
Exactly. We've talked a lot about the destructive potential.
Of these impacts.
Yeah, but could they have also shaped the moon?
Shaped it how?
Well, could they have contributed to its mountains?
Or even its internal structure.
That's a great question. Giant impacts can have huge effects.
On.
Geology and topography.
Because it could have.
Melted rock, uplifted mountains,
Wow.
even fractured the crust.
Leading to tectonic features.
It's possible some prominent features on the moon.
Like what?
The vast highlands, even those lunar swirls.
They could owe their origins to impacts.
At least in part, yes, to the shock waves and seismic activity.
Amazing to think that events from billions of years ago
I know.
could still be influencing the moon's landscape today.
It's a testament to the power of these events.
Every time we delve deeper into lunar exploration, we uncover more questions than answers. It's both exciting and humbling.
It really is a testament to the vastness of the universe.
And the need for continued exploration.
Absolutely. We need to keep pushing those boundaries.
Seeking answers to those fundamental questions.
The ones that drive our curiosity.
Well said. As we wrap up our deep dive today,
Yeah.
is there one key takeaway you'd want listeners to remember?
I think it's important to remember that the moon is not just a silent observer in the sky.
Okay.
It's an active world with a rich and dynamic history.
A history that holds clues.
Clues about our solar system and even the origins of life.
By studying the moon,
We're not just exploring another world.
we're delving into our own past, present, and future.
Beautifully put.
And for listeners who are eager to learn more,
Hmm.
we'll include links in the show notes.
Great idea.
In the meantime, step outside tonight. Gaze up at the moon.
Yes.
Consider those ancient scars.
Whispers from a more chaotic time.
Who knows, maybe one of you listening
Yeah.
will be inspired to design the next mission
To unravel the moon's secrets.
and unlock the mysteries of our cosmic origin.
What a fantastic thought.
Until next time,
Yes.
keep exploring, keep questioning, and keep looking up.